Hey guys, welcome back to the Science Factory. I'm your host, Mr. Brian, and today we're going to be learning all about surface tension. Now, surface tension doesn't just mean that things slow down when they enter a liquid. Surface tension describes the increased strength of the bond between molecules in a liquid at the liquid's surface, meaning that at the surface of a liquid, the bonds are actually stronger than they are in the rest of the liquid. For this experiment, you're going to need wax paper, some toothpicks, a pipette or some way to drop water, some food dye, and I recommend a cookie sheet or a plate to do it on. We're also going to need a little bit of soap in a small container, some water, some isopropyl alcohol, and some vegetable oil. And now you probably noticed that we dyed the water blue and we dyed the isopropyl alcohol red, but we didn't dye the vegetable oil. That's because the dye makes it much easier to see these clear liquids, but unfortunately vegetable oil doesn't work well with dye. So we're just going to have to do without dye on the vegetable oil. So for this experiment, we're going to be using this pipette to drip water, isopropyl alcohol, and oil onto our cookie sheet here. Now, I flipped the cookie sheet upside down because it's easier for filming to see the domes made by the drops. But if you're doing this at home, you should flip the cookie sheet right side up so that the edges catch any stray liquid from spilling onto the table or the floor. So the first thing we're going to do is take some water and make some nice big drips on our cookie sheet. Between each liquid, I'm going to be rinsing out my pipette because we don't want to contaminate our results. Next, I'm going to put some of the isopropyl here. Now I want you to notice that the isopropyl, even though I'm putting a similar number of drops, is much flatter than the water was. You can see that the water domes, but the isopropyl is pretty flat. This has to do with the polarity of the molecule. It's a slightly polar molecule, so isopropyl is attracted to itself, but not as much as water is. Again, make sure you rinse out the pipette between every step. Finally, for our last one, we're going to get some oil in the pipette, and we're going to drip this onto our tray as well. Now, I want you to notice that the water is much more domed than any of the others. The isopropyl alcohol and the vegetable oil are much flatter. And on top of that, we can actually move the drops of water around with our toothpick. We can make them combine into one big one, or we can collapse them if we dip our toothpick in soap and then touch them. Pretty cool, huh? Let's see if that works on the isopropyl. Not really any effect. That's because it's not a very polar molecule. Let's try it with the oil too. Nothing. So this is a major difference between polar and non-polar molecules. The polar molecules are only attracted to each other as long as there's no soap introduced. But the non-polar molecules are already collapsed and spread out, so it doesn't really matter if we introduce soap. If you're curious to learn more about surface tension and why these experiments work, we'll be adding an informational video about the science behind these experiments, and once we've uploaded that, we'll add a card for you to click here. All you need for this experiment is some pepper, some water on a plate, some dish soap, and a Q-tip. So first what we're going to do is sprinkle some pepper across the surface of the water so that we can see changes to the surface tension a little bit easier. Next, we're going to take our Q-tip, dip it into a little bit of soap, and when we touch it to the water, you should see that the differences in surface tension near the Q-tip and far from the Q-tip cause the pepper to jump. All right, are you ready? If I take the Q-tip out, it stops happening, but if I put the Q-tip back in, they shoot away again. Now remember, at this point, there's already soap molecules in the water, so the effect is becoming less apparent. Because individual soap molecules weaken the surface tension, it causes a chain reaction to occur across the water's surface. And that happens because the surface tension is now different on different parts of the surface, while the soap is spreading. Once the soap molecules are evenly distributed among the water's surface, it's not going to cause any movement along the surface anymore. And that's going to be a key factor for most of the experiments that we do today. Every time we introduce soap into the water, we're going to see that effect in a new way. For this next one, we don't want any water in the plate, and we're going to need our soap and Q-tip again. We'll also need some milk and some food coloring. Milk's a really great choice for this one because it's opaque, which means that you can't see through it very well. So the first thing we're going to do is pour a little bit of milk into a big saucer. And we want enough milk to cover the bottom of the saucer, but it doesn't need to be too thick. The next thing we're going to do is take some food coloring and put a couple of drops around the middle of the plate. So we're going to put a couple of drops of each one here. Now that you've got your food coloring in place, you're just going to take your Q-tip with some soap on it and put it into the middle. You don't need to move it around on this one, just hold it still and check this out. Whoa, super cool. Remember, this is happening because of differences in surface tension across the milk's surface. For this one, all you need is tin foil and a plate of water. But make sure that you get a new plate of water and rinse off the old one. You don't want any of the soap from the previous experiment to mess with this one. So what you're going to do first is make a boat out of aluminum foil and make sure there's no holes in it and make sure the bottom is flat. That way it can float on our thin lake of water. Next, we're going to place our boat on the water near the edge. And again, we're going to get a little bit of soap on our Q-tip, and we're going to use it this time to send the boat across the water. Pretty awesome, huh? Let's try it one more time. Now, it'll probably go slower this time because there's already soap in the water. Let's find out. Yeah, it's definitely moving slower this time. All right, it's time to head on to our next experiment. For this experiment, you're just gonna need a penny, a pipette or a straw, and some water. So we know that drops of water like to bead up on a surface, and now we know why. It's because of surface tension. But what we want to know in this experiment is how many drops can you fit on top of a penny before they spill over. I want you to pause the video for a moment and make a prediction. How many drops do you think it'll take? Wow, we got 35 drops on the penny before the water spilled over. And I don't know if you noticed, but when I was dropping the water jiggles a little bit. So it's pretty astounding to me that we're able to get to 35 drops on one penny until the water flowed over, even though every time a drop hit the surface, the whole thing was jiggling. Pretty neat, huh? Now, we're gonna try it one more time, but I wanna change something. But first, if you try this experiment more than once, make sure that you dry the penny and the plate completely between experiments. Once the water has spilled over, it's not going to bead up on the surface of the penny anymore. When you drop more water, it's just gonna flow right off. So this time we have 25 drops on the penny again, but I wanted to show you, even though we're 10 drops under the amount that made the water spill over last time, if we take a toothpick with soap, we'll see that just like in the first experiment, it breaks down the surface tension and causes the water to flow over. I love science! Now, we already learned earlier that oil is non-polar or hydrophobic, so another thing that you can do with this experiment is to try this with oil and see if that makes a difference. Now, this next one's one of my favorite surface tension experiments because it's really weird. For this one, again, we're gonna use a Q-tip with some soap on it, and we're gonna use some coffee. So we're gonna take this Q-tip, and what you wanna do is flick across the surface, and you should be able to see something really cool happen. Do you notice the bubbles sliding across the surface? Those aren't actually bubbles. Those are drops of coffee encased in small amounts of soap that are having trouble reincorporating into the coffee. It also works with milk. All right, now, obviously we don't want to drink this coffee because we just put soap in it, so ugh, not good. We're gonna put that over here. So for this one, you're gonna need a jar or a cup of water, and you'll also need something like an index card or a piece of cardboard. What we're gonna do is we're gonna place this paper on top of the cup, and keeping it flat, we're going to flip this over. Bum, 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 bum. Now, the reason that this works is partially because of surface tension and partially because of vacuum pressure. For the water to come out, air has to go back in, and since there's not any opportunity for that, water is not able to come out. So in this case, even though we would expect the water to just fall out, this card's able to hold up all this water. For the second round, you're gonna need a mesh. And you want a pretty fine mesh too, because you want the water to be able to bead up inside the mesh. Now, you wanna make sure that when you put your hand on top, that the card is going all the way across the opening. And keeping it nice and tight, we're gonna flip it. And then we're gonna remove the card. And the water is not coming out. Now, this is pretty crazy because you would expect the water to just fall right through the mesh. After all, the air can get in this time. But the surface tension of the water is strong enough to hold up all of that water, even though there's holes in the bottom. There's no tricks here. There's no saran wrap or anything like that. And I know that that's really difficult to believe, but that's why you gotta try this on your own at home to see this work in person, because it's really astounding. I have it right in front of me and I still can't believe it. This is super weird. And just to show you guys at home that we're not pulling any tricks, you can put wire right through the mesh. It's so weird. I can't even. So strange, water tension, who knew? And just to show you there's no tricks here, I'm gonna pull the mesh away and you'll be able to see all the water fall right through. This next experiment was originally part of our video, 5 experiments that you can do at home with toilet paper. You can watch that video here by clicking the card. But we're also going to include it in this video because it has to do with surface tension. You're going to need some sort of container that can hold water, some water, toilet paper, because of course we're using toilet paper for all of these today, and you're gonna need some paper clips. Before we try this experiment, we're going to need to dump some water into our container. Check. So if I take a paper clip and I throw it in water, we would expect that it sinks. And of course, it does sink. It's heavier than the water, so it sank right to the bottom. You could try that with a few more. They all sink. In science, we like to repeat experiments. Still sinking. What are some other things that might sink? Well, batteries. Definitely doesn't float. Pennies. Still doesn't float. Tiny wrench. Also sinks. What about a computer mouse? Probably best not to do electronics. Make sure you ask your parents about anything you try to float test. What about some things that float? Well, of course, there's paper. We would expect that to float, and it does. Rubber duckies with a little surfboard. He floats. Boats. Boats float if they fit. Air. Definitely floats. Feel free to try as many materials as you want as long as you have your parents' permission to find out if it floats. Some things are kind of surprising, like apples. Do you think apples sink or float? That's a good one to try at home. But what if I told you that we could make a paper clip float? That doesn't make any sense. I mean, we just saw all of these paper clips. I dropped them in and they sank. How is that possible? Well, let me tell you that it is possible to make a paper clip float. Let's go ahead and try it. So what you're gonna wanna do is get 1 square of toilet paper, and then if it's a 2-ply piece of toilet paper, make sure that you split it into a single ply. Next, you're gonna wanna take your single ply toilet paper and put a small paper clip delicately on top and really slowly lower that into the water so that the toilet paper is floating. Now, you might not be surprised yet, but watch what happens when we use this pencil to carefully push down the toilet paper. You want to do this very slowly because if you go too fast, the paper clip will fall down with it. And you see that? Our paper clip is floating, even though it's not touching the toilet paper at all. This might take you a few tries to get the toilet paper completely away, but once you do, you can see the paper clip is freely floating. Now, of course, if you touch the paper clip and you make it go below the water at all, it's going to fall right to the bottom. Seems like magic, doesn't it? As always, thank you for stopping in today. If you like these videos, please consider subscribing. Subscribing is the best way to support our channel and make sure that we can continue to provide awesome free content for you guys at home. We'd also love if you could share our channel with anyone you think might enjoy doing science experiments with us, and leave us a comment down below to let us know what kind of topics you would like to see in a future video. My name's Mr. Brian. I'll see you next time. I thought you guys might like a couple of jokes at the end of this video, just to cut the surface tension. What keeps docks afloat in water? Peer pressure. Why do some fish live at the bottom of the ocean? It's because they dropped out of school.